we present a model that predicts visual importance across different graphic designs and natural images. What catches your attention in a graphic design affects how you will perceive the information and perhaps how you will act on it. Different design classes vary in graphical structure and distribute the attention of the viewer across the design elements. For collecting ground truth importance data for our model, we repurposed the Importanauts tool used in prior work. In this interface, Amazon Mechanical Turk workers mark the image regions they consider most important to the design. While individual annotations are subjective, averaging the annotations of 20 to 30 participants generates robust heat maps similar to human attention maps. In total, we collected importance maps on 1,000 designs spanning 5 design classes. We also add natural images to the mix of our training data from the Salicon dataset commonly used for saliency modeling. Together, the 5 design classes along with natural images are used to train our model both to predict the design class and to use this class-based information towards predicting the importance map. Our model is an encoder-decoder style neural network that we call UMSI, Unified Model of Saliency and Importance. Analyzing our IMP1K dataset, we find differences in importance patterns across design types. For instance, aggregating the importance maps across all the ads in our dataset shows a central bias for the most important content, and our importance model UMSI is able to capture the same bias. Infographics tend to have a different structure, with titles occurring in the top left region and being rated as the most important element overall. And this pattern too is captured by our automatic predictions. And here are movie posters, the average importance map, and the predicted map. In all cases, UMSI learns the pattern specific to different design classes, which it leverages in order to make more accurate predictions per design class. Compared to prior approaches, our model can generalize to different image types, including natural images. Where a state-of-the-art saliency model works well for such images, an importance model trained on graphic designs does not, but UMSI performs favorably. On a graphic design importance dataset from prior work, natural image saliency models cannot generalize, and while prior importance model does well, UMSI outperforms these predictions. Our IMP1K dataset offers a broader range of design classes on which both prior saliency and importance models perform poorly, but UMSI succeeds. But importantly, because designs are a continuum and often combine natural images with graphic design elements and text, UMSI can adapt to the design process to offer iterative predictions of importance that can be used within interactive tools to offer design feedback and guidance. As a proof of concept, we test UMSI within an interactive design tool. We developed a bare-bones research prototype with minimal design support in order to evaluate the ability of UMSI when coupled with a genetic algorithm to offer prescriptive feedback. A user assembles a design on a canvas and explores the predicted importance of the design elements. By interacting directly with the importance score of an element, a user can specify whether to increase or decrease the importance of the element in the final design. A genetic algorithm operating in the backend receives continuous feedback from UMSI to shuffle and resize the design elements. The application produces new variants to reflect the user's objectives. While this is only a bare-bones demo, it offers a promising new direction for importance models like UMSI to offer AI-assisted guidance within graphic design tools. As another demonstration for importance-driven graphic design, we worked with developers of a commercially available design tool to integrate UMSI into a design reflow pipeline. Users can assemble their designs and interact with individual design elements. The design tool supports alternate layout suggestions to automate the reflowing of a design to a new aspect ratio. We pass the full design to our importance model in the back end and constrain the reflow engine to conserve the importance ranks of the design elements. We aim to maintain the designer's intention. What was most important in the original design should remain most important in the reflow. Further details are in the paper. We ran the generated reflow variants through a crowdsourcing task to evaluate how importance-guided reflow using our model compares to default reflow in the existing application and compared to importance-guided reflow using the prior state-of-the-art. The design results produced by using UMSI in the back end of the reflow algorithm outperformed the other two approaches. UMSI, trained on both natural images and graphic designs, ranks elements by importance in a perceptually meaningful way. In this work, we have shown the generalizability of our model in predicting importance across graphic designs and natural images, making it suitable for use within interactive design workflows. Our proof of concept demos show the promise of using importance predictions for AI support within design tools, and by making both our model and dataset publicly available, we hope to facilitate such future applications.